Hey scientific genius people, how are you today? So today we are going to discuss about the thermal expansion in solids, and we would be covering the linear, superficial and cubical expansion coefficient also. So this is how our lecture flow is going to go. We are going to understand about coefficient of linear expansion, then superficial expansion, and then cubical expansion, and factors affecting alpha, beta, gamma. And then we will also understand about that on what factors alpha, beta and gamma does not depend. So basically I would be talking about alpha, and then I would be generalizing the same things for gamma and beta, because it doesn't require a separate explanation. Once you understand what is alpha, the same concepts would be applying for beta and gamma as well. So let us begin. There are three types of objects first. One-dimensional object which only has got length, two-dimensional object which has got length and area both, and three-dimensional object which has got length, area and volume all three. So I may consider a very thin rod. So a thin rod has got only length. I cannot find its area. So length is present but area and volume are not there. In superficial expansion, I am going to consider a very thin sheet. So it has got length and breadth. So it is also having length, and length times breadth, this part is the shaded part, is area, but it doesn't have volume. It has a negligible volume because it will have some thickness, but we are not considering that, right? And in case of cubical expansion, we would be having a three-dimensional object like a cube which has got length, breadth and height. So length is also present. This is the shaded area. So 6 such shaded area would be there. So area also is present and volume is also there. So linear expansion would be taking place in case of very thin rods, superficial expansion in thin sheets, and cubical expansion in a cube-like objects, or you may also consider cuboid. So let us talk about the linear expansion first. So here we have a simple picture having copper rod. So we have two copper rods, a smaller copper rod having say some length L01 and say, let me take very easy length for you so that you can well understand these concepts. Let me consider this length as L1 and this length is L2. So L1 and L2 are original lengths of the rod, and as you can see that 1, 2, 3 and 4. So there are 4 atoms present inside this length. Actually these all things are assumed by me. It is not practically the case that there are only 4 atoms in a rod. There are crores and crores of atoms inside a rod, but I am only considering 4 atoms. And the distance between these atoms is also very, very tiny. They just almost touch each other. But here I am showing some space so that we can understand the concept in a better way. Actually these things does not exist. So two copper rods, length L1, length L2, and L2 is bigger than L1. So since this rod is larger, this rod will be having too many atoms but having the same distance 1 centimeter as over here, because the material is same. And suppose the initial temperature of the rod is 27 degree. Here also this temperature is 27 degree. And suppose I heat it till 57 degree Celsius. So the rise in temperature, this is initial temperature Ti, this is final temperature Tf. So temperature final minus temperature initial is 30 degree. So change in temperature is 30 degree Celsius. Or I can also write it down as 30 Kelvin, difference doesn't matter, and that's why I have mentioned it over here for same rise in temperature. So two rods having different lengths, same rise in temperature on heating. What happens is this gap between these two atoms becomes 2 centimeter. Since the material is same, so this gap also becomes 2 centimeter. So this rod increases in length by this much amount, whereas this rod increases in length by a longer amount. So let me call this as delta L1 and this is delta L2, where delta L1 and delta L2 are the change in the length, increase in the length. Now I have shown a very factual situation over here. Actually the rod increases from both the sides, but I am showing over here that the length of the rod increases from one side for better understanding. So we can see that smaller rod expands by smaller amount and longer rods they expand by longer amount, right? Bigger amount. So from here we can derive a conclusion that delta L, which is the increase in the length, is proportional to the original length. That is L0. L0 over here is equal to L1 and here it is equal to L2. So L0 is the length before heating. So longer the rod you take, more is the increase in the length. That is what is the meaning till here. So that is the first factor that we have discussed, that increase in the length depends upon the initial length of the rod. So let us move on. Here we have two rods, same copper rods, both are copper rods, but both have equal lengths as well. Before heating, the length of this rod is L0, this is also L0, but the increase in temperature over here, this rod is heated by, the difference in temperature is 20 degrees Celsius, and here the difference in temperature delta T is 40 degrees Celsius. That means you are providing more heat to this rod compared to this rod. So more is the rise in temperature. So this is the increase in the length here, and this is the increase in the length. I would like to tell my viewers, practically the rods cannot become this much long. This is just for your understanding. So the increase in the length is very negligible, right? So it is clearly seen that increase in length is directly proportional to increase in temperature. More the rise in temperature, more is the increase in length. So directly proportional behavior. Third thing is the type of material. So here you have copper, say for example this is iron rod and this is copper rod, correct? Initial lengths are same, L0, L0. Rise in temperature is same for both of them, but still if you look here, one rod is expanding more than the other rod, like copper is expanding more compared to iron. It is because the material, you are changing the material, so the expansion rate in both of them will be different. So even though all other situations are same, like same initial length and rise in temperature is same, still since the substance is different, they will show different kind of behavior in expanding. So that means delta L also depends upon type of substance. Correct. Now combining all three things, let us try to jot down all the things in a proper way. Mathematics says that if x proportional to A, x proportional to B, then x is also proportional to A multiplied by B. If I want to remove this proportionality sign, so x would be equal to some constant k multiplied by A into B. So it's a rule in mathematics that if you want to remove this proportionality sign and if you want to put is equal to sign, you have to put a constant. This constant may change as per this equation. If you take a different equation, the value of constant will change. The constant may or may not have units. Same thing over here. We have seen that delta L was proportional to L, L0, the initial length of the rod. Delta L is proportional to rise in temperature. So if I combine both of these, delta L would be proportional to L0 multiplied by delta T. Now, if I want to remove this proportionality sign, delta L is equal to some constant which is called alpha times L0 times delta T. This alpha is called coefficient of linear expansion. So we actually come to a very important expression, that is change in the length, this is change in the length. This is length before heating, original length of the rod, and this is the rise in temperature or fall in temperature. I am not telling this as a rise in length, because if you heat, then this would be rise in length. If you cool, this would be shortening in the length. So generally speaking, this is the change in the length before heating, and this is the change in temperature, right? If this is the rise in temperature, that means you are heating the rod. If you are heating the rod, then delta L would be the rise in the length. Alpha is a constant. Now alpha is equal to delta L upon L0 times delta T. Correct. So these two were in multiplication, they will go down here in division. Now anyhow, change in the length is measured in meter. Initial length is also measured in meter, and SI unit of rise in temperature is Kelvin. So meter getting cancelled. So 1 upon K is the SI unit of alpha, or you can also write down this as K raised to minus 1, Kelvin raised to minus 1. But as discussed earlier, that delta T is the change in temperature, and change in temperature, if you write it down in degree Celsius or in degree Kelvin, it doesn't matter. So I can also write down alpha to be 1 upon degree Celsius. So it can also be written as degree Celsius raised to minus 1. Alpha is a very small number, and alpha changes if you change the metal. So alpha for copper is something else, and alpha for steel would be something else. And make sure that this is delta T. So if the unit of alpha is changed from degree Celsius to Kelvin or Kelvin to degree Celsius, it is not going to affect us. Now let us try to actually understand the meaning of coefficient of linear expansion. So we have studied that the initial length of the rod is, say, L0, and if I hit this rod such that delta T is the rise in the temperature, then this rod will increase by some amount, that is delta L, and this delta L is given by delta L is equal to L0 alpha into delta T. From here, if I find out the value of alpha, it is equal to delta L upon L0 into delta T. Now what am I assuming over here? I am assuming that this L0 is 1 meter. So the initial length of the rod before heating was 1 meter. So the rod which I took was 1 meter. Say it is 1 meter rod of copper. Then I heated such that rise in temperature was 1 degree Celsius. So say this is 1 degree Celsius. Initial temperature was 27 degree, and I heated such that the final temperature became 28 degrees Celsius. So this delta L, the rise in the length, the increase in the length itself is called alpha. So alpha would be equal to delta L if L0 is 1 meter and delta T is 1 degree Celsius. Correct. Now suppose alpha value for copper is 117 into this is the rough value, 10 raised to minus 6 degrees Celsius raised to minus 1. Suppose this is the value of alpha for copper. Now what does this mean? We have to understand this, right? So if the value of alpha is given, which means that you had taken 1 meter rod of copper, 1 meter rod of copper, and you heated this rod such that its temperature went up by 1 degree Celsius. Then this rod would have increased in the length. This increase in the length, delta L, is equal to the same magnitude, 17 into 10 raised to minus 6. But since your rod was in meter, I would write down this in meter. So this is the meaning of alpha over here. So I have 3 cases over here in front of you, and alpha of copper I have given correct value over here, 17 into 10 raised to 6 minus 6 Kelvin inverse. I can also write this as degree Celsius raised to minus 1. Correct. Okay. This rod is of 1 meter. There are 3 cases over here. So this rod, which is shown in A, has got length 1 meter. This is 1 centimeter and this is 1 millimeter. All 3 rods are of copper only. So now if I want to calculate delta L is equal to L0 into alpha into delta T, for first rod A, I am going to apply this equation. So L0 is 1 meter, alpha is 17 into 10 raised to minus 6. I can also write down in degree Celsius raised to minus 1. So 1 upon degree Celsius into rise in temperature is 1 degree Celsius. Degree Celsius getting cancelled. So my answer delta L is 17 into 10 raised to minus 6 meter. So that means the increase in the length for this rod delta L is 17 into 10 raised to minus 6 meter, because the rod was in meter. So final answer is in meter. Now if I want to apply the same equation for B rod, then delta L, that is equal to L0 alpha delta T. Instead of L0 I am going to put 1 centimeter. No need of converting 1 centimeter into meter. This alpha is 17 into 10 raised to minus 6, 1 upon degree Celsius, multiply by delta T is 1 degree Celsius, because rise in temperature in all three cases we have assumed 1 degree Celsius. Again degree Celsius getting cancelled, and my answer is 17 into 10 raised to minus 6 centimeter. So this rod also increases by some amount, and that delta L is again 17 into 10 raised to minus 6 centimeter, because you took the rod in centimeters. Again I need not to do the whole entire calculation. If I do this calculation, delta L would be same as alpha, and that is 17 into 10 raised to minus 6 millimeter. So hopefully you have understood what I mean to say. No matter what is the length of the rod, 1 centimeter, 1 meter or 1 millimeter, if you heat the rods by 1 degree Celsius, then the change in the length, the increase in the length is alpha magnitude wise. Then you substitute the unit in the unit which you already had. So meter, so meter. So here it was centimeter, so centimeter. Millimeter, so millimeter. Correct. So alpha does not depend upon the length of the rod. If you are having 1 meter rod, this would be the increase in meters. If you have 1 centimeter rod, same would be the increase but in centimeters. If you have 1 millimeter rod, same would be the increase magnitude wise, but the unit would be millimeter. Correct. Now so let us now talk about the factors on which the coefficient of linear expansion doesn't depend, because these are all the kind of misconceptions that we develop. So it does not depend upon the length, right? So let's understand that this is rod A, this is rod B. Rod A has length, say for example rod B has length L0, so this length is L0, and this length is suppose 3 times of L0, that means thrice the length of the rod B. Correct. Now we had already discussed that delta L is proportional to L0, which means if I increase the temperature of this rod by 1 degree, this rod will expand by delta L amount. But if I heat this rod by same 1 degree rise, this will be thrice of delta L, because this length, if I make this length double, then the increase in the length will also become double. That is what is the meaning of proportionality. So which means if I separately calculate delta L upon L0 into delta T, that is alpha for this rod, and alpha for this rod is 3 times delta L, because this length is triple the length of this length, so there will be thrice the expansion compared to the rod B. So alpha for rod A and alpha for rod B is equal to 3 times L0 into delta T is same. So again this 3 and 3 getting cancelled. So alpha A is equal to alpha b does not depend upon the length of the rod. So if I make this rod 5 times longer, then the expansion will also be 5 times. Anyhow, these 5 and 5 will be getting cancelled. Alpha will not be affected, provided these are of same material. So here I have considered that both rods are of copper and copper. Delta T is same and it does not depend upon the length of the rod. Second thing is regarding the rise in the temperature. So I am keeping the length of both the rods same, L0, this is also L0, and both the rods are made up of copper. And since we have discussed this, delta L is proportional to delta T. That means more the rise in temperature, more would be the expansion. This is rod A, this is rod B. I am heating it by delta T. So this is the expansion in the length delta L. But suppose this delta T is say 1 degree Celsius, and here if I take delta T as 3 degrees Celsius, so here delta T is thrice the delta T of the rod B, 3 degrees Celsius. So since if I make this double, this will also become double, which means if I make this as 3 times delta T, so this increase in the length will also be 3 times compared to the rod B. So this delta L will again be 3 times of delta L. So again, if I separately calculate for both, delta L upon L0 times delta T is equal to alpha for rod B, and for rod A the expansion is thrice, so it is 3 times delta L upon the L0 remains the same, but here the increase in the temperature is 3 times compared to rod B. So anyhow the 3 and 3 is going to get cancelled. So again we get the same answer, alpha A and alpha B are the same. So if I rise the temperature of this by 10 times, then the expansion also will become 10 times. Anyhow 10 and 10 from top and bottom are going to get cancelled. Here we have a sheet of iron, and for the sheet of iron, this is the sheet of iron having area, say for example A. So this area is A, and say the length is L and the breadth is B. So the initial area is, let me consider A0 at this temperature. So at this temperature the final area would have become bigger. So this was the initial area and this is the final area, and this shaded portion is the increase in the area, that is delta A. Again I won't be repeating the entire story, but delta A proportional to A0, that means if you would have taken bigger sheet, then the area expansion would have taken bigger. Again delta A proportional to delta T, so delta A is proportional to A0 into delta T. If I want to remove this proportionality sign, delta A is equal to beta into A0 into delta T, where this is called coefficient of superficial expansion, beta, correct, and beta is twice of alpha. So for students below 10th grade you have to just accept it, because the proof comes in thermodynamics in grade 11, right? So if you are given the value of alpha, you can just double it up, you will get the value of beta, and beta is equal to delta A upon, because these two are in multiplication, they will go down here in division, again delta T. The unit of delta A is meter square, unit of A0 is again meter square, so getting cancelled. Again 1 upon Kelvin is the SI unit, so Kelvin raised to -1 is the unit of beta, correct. Same the case for volumetric expansion. So here we have a cube of length L, or we may assume cuboid of length, breadth and height LBH. So initial volume is equal to L into B into H, that is V0. At this temperature, the new volume, the volume has expanded. So this is the old volume, this is the new volume. So the shaded part, I cannot shade it completely because I am working on a 2-dimension screen and I have to show 3-dimension increase in the volume. Again, the increase in the volume, the shaded portion is delta V, is proportional to original volume. More bigger the cube, more will be the expansion. Again, delta V proportional to delta T. Again, delta V proportional to V0 into delta T. If I remove the proportionality sign, delta V is equal to gamma, coefficient of volumetric expansion or cubical expansion, V0 into delta T. Again, from here the gamma value is equal to delta V upon V0 into delta T. SI unit of this is meter cube. This is also meter cube, getting cancelled. So again the unit for gamma is Kelvin raised to -1. And gamma is 3 times of alpha. Again, we are supposed to remember this without proof. Or we can also say that alpha is to beta is to gamma is 1 is to 2 is to 3. So hopefully guys, I have explained most of the topics with clarity, and hopefully you have enjoyed my explanation. Please do subscribe to my channel, and if you have any doubts, do comment in the comment section. Thank you for watching the video.